Hello, we are Brandon Munoz and Josue Cortez, and today we will explain to you about a method called elastic beam method, and which is also commonly known as double integration method.
Generally, we can say that this method is one of the first seen in structural analysis, since due to its structure and methodology, it is usually one of the most simple to understand, since minimal knowledge of statics and mechanics of materials is needed. Taking this into account, a question arises. Why do we use this method? This method is mainly used to calculate two types of deformations that can occur in a beam, whether it is simply supported, embedded with cantilevers, without cantilever, with distributed loads, or even that the beams can have different geometric shapes and be made of different materials.
These two deformations are the linear displacements and the angular displacements. These two are the main ones when doing this method. Since to do a structural analysis, we must know what deformations an element will have when subjected to loads and what. Why do we want to know this? Well, with this data, we can know if our structure is safe and complies with the guidelines established by construction regulations, since it depends on this whether the projects are approved and carried out.
Now that we know what this method is used for, I will explain where these equations come from and how we can use them when analyzing and solving a problem. The base equation of all this arises since having a beam we are looking for balance, and from here arises the first differential equation, which represents the balance in the beam since we use the moment equation, and it is the following. The bending stiffness, EI, multiplies the second derivative with respect to x is equal to the moment equation with respect to x. As can be seen, there is a term EI, which represents the bending rigidity, and we can separate this into E, which represents the modulus of elasticity of the material with which the beam is made, and the I represents the moment of inertia of the beam area.
We can write it as follows. The first derivative with respect to x is equal to the integral of the moment equation between the bending stiffness with respect to x is equal to the angular displacement. If we integrate the equation again, we are now left representing the linear displacement, and it is written as follows. Y is equal to the double integral of the moment equation on the bending stiffness with respect to x. At the same time, it is equal to the linear displacements,
and now represents the distance that the beam moved. Although we observe education in the previous equation, we are left with y equals sign. We can explain this in the following way. If we remember a two-dimensional Cartesian plane, it has two axes, the x-axis and the y-axis. The x are in charge of measuring what moves from left to right, and the y measure the displacements we have up and down. Therefore, the second derivative represents the linear displacements with respect to the y. In other words, the deformation that the beam will have upward or downward.
An example applying this method is the following. If we have a beam with a point load in the middle, the beam is simply supported 4 meters wide. Then first, we calculate the reactions in the two supports. Once the reactions have been calculated, we now proceed to make two sections in the beam to be able to analyze and calculate the displacements. The first section begins at the support and ends, where we have the point load, which is at 2 meters, and now we proceed to calculate the moment equation. Already having the moment equation, now if we apply the double integration method, which tells us that the integral of the moment equation between the bending stiffness is equal to the angular displacement, so it will give us an equation and we will be left with a constant. Now we integrate the previously calculated equation again to calculate the linear displacements, and now we will have another equation and a second constant.
We do the same procedure with section 2, calculate the moment equation, and then integrate this to find the equation to calculate the rotations, and integrate again to calculate the linear displacements. As we well realized, we were left with 4 equations with 4 unknowns. And now, what do we do with these? Well, now we have to see in which situations we have some data that can help us. A clear example is that the linear displacement in A and B are equal to 0. Therefore, we rely on this, and with equations 2 and 4, which are what help us calculate the displacements, we can substitute where there is an x. We place a 0, and now we solve, and we are left with C2 equal to 0. We do the same with equation 4, and it gives us the same result, so C4 is equal to 0.
Now, how do we calculate the other two constants? Well, just as we observed that the displacements in the supports are equal to 0, we can say and observe that the displacements are equal at one specific point at the end of section 1 and when section 2 begins, so we can equalize the rotation equations and linear displacement of the two sections and thus obtain or calculate the constants C3 and C1. And now, having the value of the four constants, we can now directly calculate the displacements that we can have along the beam.